Welcome back. We just got started to look at the mathematical formulation of the spontaneous instability of an ultra thin film, which is coated on a rigid or a solid substrate. The film thickness is h. H is a function of x and t, and so essentially we are talking about a film like this, where the thickness can vary spatially as well as temporally. The continuity equation we have seen is this, we have talked about in detail. The governing equation based on the force balance remains to be the Navier-Stokes equation for x and z components, which are given here. Only additional term that what has come in is the effective interface potential, which we have considered. Because of the non-planarity of the top surface, we have assumed the axisymmetric fluctuations at the surface, and that gives results to the Laplace pressure, which is taken care by the long wave approximated Young Laplace equation, which has this particular form. And we additionally have the kinematic boundary condition which sort of correlates the components of velocity at the leak-free surface. That is, it combines us and ws. Okay. So, these are all the equations that we will need to understand the mathematically to distinguish how the instability of a thin film can be sort of used or can be understood. The next thing that we will do is what is known as order of magnitude analysis. This is a very common practice that is done in sort of which gives an idea about the scaling or the orders, and is very common in heat transfer and as well as in fluid dynamics. So, if I am sure you have done order of magnitude analysis in some setting or the other, but if you have not done it, just go through it from some textbook of let us say fluid dynamics like or heat transfer like Adrian Bejan, for example, that if you look at the chapter on boundary layers in your fluid dynamics or in your heat transfer, I am sure you will come across this concept of order of magnitude analysis, because what you regard as the boundary layer approximated Navier-Stokes equation, where if you are talking about a 2D flow, you preferentially neglect one of the terms. If you remember carefully, this term is neglected from the x component. It has nothing to do with our derivation. This term is neglected from the x component Navier-Stokes equation within a boundary layer. And if you try to understand the origin, what this some chemical engineering textbooks of course refer to this as the boundary layer approximation, but if you look carefully, this whole concept of this so called boundary layer approximation comes from nowhere other than order of magnitude analysis. So, in other words, this analysis gives a relative scale of different variables. So, let us say I will also make your concepts give you some simple concepts. We have a film like this, and this is our coordinate system we have chosen, x and z. We have identified that the film thickness is h. Of course, you have created the film can be very thin, because we are talking about a thin film. where we have the interfacial interaction to be active. Therefore, there is no doubt the film thickness is very low, but the film can be spread over a large area because you are spin coating. So, you can't create it over a few nanometer area, you are taking a macroscopic object over the entire area, the film is nicely coated. So, what it means that the expanse of x is much higher than the expanse of z in your system. So, your x sort of stretches is the entire zone over which the film is coated. Let us say this is of the order of L. L is some sort of a length, let us say this is L. Okay. In contrast, your expanse of Z is Z stretches from only 0 to H, and H is the film thickness. So, from the physics of the system, what you can say is that first thing you can say that H is of course much smaller than L, because you are talking about a film. Why you say this? This comes from the basic system configuration. Film is few maybe tens of nanometer thick. In contrast, the film is cast over few centimeters square area. So, what it implies that the lateral dimension x is much larger as compared to the vertical dimension h. So, we can write the order of x, that is how it is written, OX, that is the order of x is that of L, and the order of z is that of h. Therefore, immediately what you can say that order of z is much smaller than order of x. So, this is how typically an order of magnitude analysis would be proceeding. So, let us assume that, but this is some sort of a very approximate approach to sort of get a qualitative idea about the magnitude or the scale of different systems. Okay. But still it works remarkably well for systems, for unknown systems, or to identify the importance of different terms in a particular system, and that is why we will discuss the order of magnitude analysis. Okay. Now, let us assume that the order of u be that of u, okay, and we also have the order of x to be L, order of z to be h. Okay. Now, if you look at the continuity equation, which is del u del x plus del w del z is equal to 0, that is order of u by order of x is of the order of w divided by order of z. Do not have to worry about the sign and all that, this is just a qualitative order. Do not forget one thing, this is a simple rule of thumb, that in a continuity equation which is direct consequence of mass balance, so no term can be neglected in this in a continuity equation based on order of magnitude analysis. But what it gives is this, use a fresh page. What we have is order of x is that of L, order of z is that of H, order of u we have argued assumed it to be the order of u, and then we have this is our continuity equation. Therefore, we get order of u by now out of the 4 orders that are involved here in this equation, you see that 3 are known, that is x, z and u are known. So, if you plug in those orders, what you can get, the order of w is h by L times order of u, which means that what is the significance of this mathematical statement? It means that the magnitude of w is much smaller, or the order of magnitude of w much smaller as compared to u. Okay. So, if we assume h by L to be equal to epsilon and further assume order of u to be equal to 1, what we get, order of w is of the order of epsilon. Okay. Now, after obtaining the order of w from the continuity equation, let us investigate the kinematic boundary condition with the order of magnitude analysis. So, this is the kinematic boundary condition we have. So, the equation is okay. So, we plug in the respective orders, order of h is now known, h or z or whatever. Yeah. So, this is h by order of t, second one is order of us is of the order of 1, so first term is this, second term is 1, this is h and x is L, and w is also of the order of epsilon or h by L. So, this is the order of the first term, third term. So, you can see that the orders of the second and third term, sorry, this is u, this is u and this is also u, but u is of the order of 1. So, this is h by L, this is perfectly fine. So, you can see that the second and third term both have the order of h by L, and the first term is h by order of t. So, these two now matches. So, what comes out, the order of time is of the order of L. Okay, and now we know that h is L is large. Therefore, the time scale, the magnitude, the order of the time is large, or in other words, the dynamics of the system is slow. What it implies physically is the dynamics is slow. Okay, so this is the other implication of this is the implication of performing the order of magnitude analysis on the kinematic boundary condition. Now, if we look at so it is large means that we take that order of time is epsilon inverse. Epsilon is small, so the order of time is epsilon inverse, and what it gives is, so these are the orders we have. Okay. So, here are the orders we have. Order of u is u, order of w is epsilon times u. We normalize the order of u to be equal to 1, therefore, order of w is equal to epsilon. Order of x is L, order of h is h. We normalize the order of h to be equal to 1, therefore, order of L is or order of x is epsilon inverse, and we also have order of time is epsilon inverse. Okay. So, having these orders now ready at our disposal, we now try to start investigating the Navier-Stokes equation, the x component. Navier-Stokes equation. So, this is the equation we have. Okay. Now, if we plug in the respective orders, we will find the first term will have an order of 1 corresponding to u and epsilon inverse. The second term will have an order of the u is 1, again 1, and x is epsilon inverse. Third one is w is epsilon, u is 1, z is 1. This term remains, we do not do anything because we have no idea about their order, and out of these two shear stress terms, the first term you see is u is 1 divided by x del u del x. So, x is epsilon inverse, and again a differentiation with respect to x. So, epsilon to the power minus 2, and the second term is u is 1 and z or h, this is z or h is also 1. So, this order is 1. So, if you simplify, this is epsilon, this is epsilon, this is epsilon, and this is epsilon square. So, based on an order of magnitude analysis for a thin film, we see that from the x component Navier-Stokes equation, all these terms sort of are insignificant, and therefore, the final equation, governing equation, takes the form of we define a capital P as a non-gravitational pressure as P plus phi. Therefore, the equation takes this shape of del P, del capital P del x is equal to mu del 2u del z square, or in a compact form one can write P x is equal to mu u z z. Okay. So, this is what we get from an order of magnitude analysis of the x component Navier-Stokes equation. Now, this is going to be the final governing equation, and it is going to be very important also. Now, it is apparently a steady state equation. However, the reality is it is a pseudo steady state equation as u itself is an implicit function of time. Okay. Now, let us investigate the z component Navier-Stokes equation. And the equation is del t u del w del x plus del w we have used the expression of the non-gravitational pressure combining p and phi straight away. Now, if you plug in the respective orders, what you will find here is that this first term w, the order of w is anyway, let us have these orders here. So, order of w is epsilon divided by epsilon inverse. Order of u is 1 epsilon, and order of x is epsilon inverse. So, this is w is epsilon, omega is epsilon, this is 1, this we leave untouched, and this one turns out to be omega is epsilon divided by epsilon inverse. Epsilon inverse. Remember that this type of a term del 2 w del x square, one looks at the order like del x of del w del x. So, the first we look at the order of del w del x, it is epsilon by epsilon inverse, and then again look at it as del x. So, it is epsilon divided by epsilon inverse, and the final term is w is, so essentially we are looking at del z of del w del z. W is of the order epsilon, z is of the order 1, so 1 into 1. So, overall what we find that this has an order of epsilon square, epsilon cube, and this is epsilon. So, all the terms sort of are insignificant, and what emerges out that dp dz is equal to 0, which means that p is not a function of z. Now, this is significant, that is, there is no distribution of pressure across the film in z direction. This will be another very significant finding, as we will see. So, now that sort of brings us back to the governing equation, which is this we go back to this equation, which is the simplified x component Navier-Stokes equation, which is mu into del 2 u del p del x. So, we will write down the appropriate boundary conditions as the time comes. So, the other thing that I would just like to highlight is that the consequence of before I move further, sorry, I forgot to mention it, consequence of del p del z is equal to 0 is h sorry, not del p del z is equal to 0 is that h is a function of x t but not a function of z. So, h is not a function of z. This is important. Okay. Now, this is the simplified Navier-Stokes equation. So, you integrate it once with respect to z, you get mu del u del z is equal to p x z plus c 1. Now, first we invoke the first boundary condition we invoke is the 0 shear boundary condition, which gives that at the free surface the shear stress is 0. So, at z equal to h, mu del u del z is equal to 0. Therefore, you substitute what you get is the value of the constant of integration C 1 as minus p x into h, and if you substitute that, you get mu del u del z is equal to p x z minus h. You integrate it further, we get mu into u is equal to p x into z square by 2 minus z h plus c 2. At this point, we invoke the no slip boundary condition. That is at z is equal to 0, u is equal to 0. If you substitute that z is equal to 0, u is equal to 0, what you get is C 2 equal to 0. Therefore, you get mu u is equal to p x into z square by 2 minus z h. So, I will just quickly repeat as to what we have been trying to do before proceeding further, so that you do not get confused. So, what we started to look at after we got to all the relevant equations is that these are the set of equations, set of the governing equations we have. We will continue our discussion once we do a quick recap at this stage. So, we are looking at the hydrodynamics of a free surface of a liquid film. So, what we are looking at interface this is what we are trying to investigate, of a thin film and based on refer to the previous class. So, you will understand what are the equations we need to talk about. So, we have the equation of continuity, we have the x component Navier-Stokes equation, the z component Navier-Stokes equation. The only additional terms you find are the effective interface potential, or the phi, which arises out of the interfacial interaction between the two interfaces, because we are talking about a thin film. So, this interaction that originates, which can be van der Waals or which can be other forces, that will be taken care of through the expression of phi. So, please understand that this form, in this particular form, the present form, the Navier-Stokes equation is not limited to van der Waals interaction alone. Okay. It is the Navier-Stokes equation which incorporates the effective interface potential, that is, it is valid for any system where there is an additional interfacial interaction. Okay. Now, the expression of phi, you can have terms which can represent only the van der Waals interaction, or you can have additional terms also that can take care of additional interactions, let us say acid base, polar or steric interactions. Now, you can use this form of Navier-Stokes equation for all your fluid dynamics derivations you have done so far, because do not forget that phi will definitely be a function of h, which is the film thickness, and if your film thickness is higher, in most cases what is going to happen, that h will have some exponential power and it will be in the denominator. So, in most cases what is very likely to happen is that for higher values of h, phi will tend to 0. Therefore, this term has no significance in the macroscopic derivations or deductions, and therefore, we often tend to neglect it, but there is absolutely no problem if you have this term intact in your macroscopic derivations as well. Subsequently, we talked about the fact that the interface we are talking about is not a flat interface, and therefore, we have these surface fluctuations or the undulations, which results in a liquid interface which is non-planar. Therefore, you have these resulting into local Laplace pressure distribution, and since we have a Laplace pressure, so we invoke the equation, the Young Laplace equation for an axis symmetric undulation. We assume that the undulations we are talking about at the surface are axis symmetric. Then all we did was to invoke the condition for what is known as the long wave instability, that essentially implies that del h del x is very, very less, or it is close to 0. So, once you plug that into your expression of the Young Laplace equation for an axis symmetric surface, this is the form of Young Laplace equation that you are left with. Then we talked about the fact that now that you have undulating top surface, therefore, the surface components of velocity u and w are not 0, and therefore, they are finite. So, we needed an expression which will sort of combine the function or provide a functionality between us and ws, and that is precisely what is given in the form of this kinematic boundary condition. The derivation we have done in the previous class. So, if you are still confused, I would like to request you to repeat that video once more. Tell your instructor to repeat the video once more, so that you get an insight of what the kinematic boundary condition is. So, these are the 5 governing equations what we have, based on which we would like to investigate mathematically the necessary condition or the criteria for the or how the a free surface of a thin liquid film behaves. Okay. So, this is how we started off. Then I introduced you to the concept. I guess it is known to most of you, the concept of the so called order of magnitude analysis, which essentially gives you some sort of an idea about the expanse or the relative magnitude of the individual terms. So, we just briefly talked about how to perform an order of magnitude analysis, and I told you to refer to some derivation related to boundary layers in any standard textbook like Incropera, DeWitt, or even McCabe Smith maybe, but Fox McDonald for sure, Adrian Bejan of course, is one of the key figures of order of magnitude and popularizing the order of magnitude analysis. His heat transfer book, or convection heat transfer, that's the book where he talks about the boundary layer, the order of magnitude analysis in great detail, and use it for various deriving various mathematical functionalities. So once we started to look at the order of magnitude analysis, we individually did the order of magnitude analysis of all the equations that we are considering. The first we use the order of magnitude analysis in the continuity equation, which gave us the fact that the order of W, that's the z component velocity, is much smaller as compared to order of u. And then we looked into the order of magnitude analysis of the kinematic boundary condition, which told us that the order of time is epsilon inverse, that's time is slow. Then we looked at the order of magnitude analysis of the x component Navier-Stokes equation, which gave us this simplified form that all other terms are much smaller as compared to these terms. So this is our final governing equation. And we also looked at the order of magnitude analysis of the z component Navier-Stokes equation, which gave us del p del z is equal to 0, which eventually tells us that h is not a function of z. So with that, we started to look at the simplified x component Navier-Stokes equation, and we have integrated it twice already with respect to z, and invoked appropriate boundary condition. The first boundary condition we invoked is that of a zero shear boundary condition, which tells that at a free interface the shear stress is 0. So we plug that in to get the first value of the first constant of integration. And the second boundary condition we have invoked is the no slip boundary condition at the film substrate interface, which gives us C2 is equal to 0. So at this point, before we started this quick recap, we have reached up to this stage where we have got an expression that mu u okay. Now what we can do is that we understand, so this equation gives an expression of u in terms of h. Z. Now, if you plug in Z equal to h, what we actually get is the value of u at the free interface. So, for Z is equal to h, from this equation we will get the value of us, and which turns out to be us is equal to one by mu into px h square by 2 minus px h square, or it turns out to be minus 1 by 2 mu px h square. Now, we relook at the continuity equation. Which gives del u del x is equal to minus del w del z. Okay. Now, we have an expression of u is equal to 1 by mu into p x z square by 2 minus p x h into z. Now, if you look carefully in this expression on the right hand side, p x and p x into h or p x and h both are functions of x. Z is not a function of x. Okay. So, what we do, we take this expression of u and find out that partial derivative del u del x. So, from here we get del u del x is equal to 1 by mu into p x x z square by 2 minus p x into h del del x of p x into h into z. Okay. Which now we have that del u del x is equal to minus del w del z. So, we do that substitution and we get del w del z is equal to minus 1 by mu p x x z square by 2 minus p x h x z. If we now do an integration, what we are left with now is w is equal to minus 1 by mu p x x z cube by 6 minus p x h x into z square by 2 plus c 3. At this point, we invoke the third boundary condition, which is that of a solid impermeable wall, that is at z is equal to 0, w is equal to also 0, which gives us C 3 is equal to 0. Therefore, we are now left with another expression of w in terms of z. Okay. So, if you now substitute the expression, if you now substitute z is equal to h in the above equation, what you will get? You will get an expression of w s, which turns out to be minus 1 by mu into p x x h cube by 6 minus h square by 2. So, what we have now is in the from the previous expression we got, we have an expression now of u s in terms of h, which is we have an expression for u s from here, which is and we also have an expression for Ws now. Okay. So, once we have these two expressions in hand, we can now invoke the kinematic boundary condition, okay, and which has this form, which is here, and which is which gives del H del T plus US del H del X is equal to Ws. Now, if we substitute the expression, so what the strategy now is to substitute the expressions of US and Ws into the kinematic BC. And once you do that, what you get is del H del T del H. So, you substitute the expression for this Px H square by 2 mu into Hx is equal to minus 1 by mu H cube by 6 Pxx minus H square by 2 H Pxx. So, you just substitute this expression over here on the right hand side, which contains the Ws, and on the left hand side you have Us into del H del X. So, once you do that, all you do is you need to do a little bit of algebraic manipulation, particularly on the right hand side. So, it is minus 1 by mu H cube by 6 into Pxx minus H square by 2 into so this differential we now want to break up H Pxx plus Hx Px, because both H and P are functions of x. So, if you do that, you find that these two terms actually combine, this and this, and it results in this term on the other hand has an Hx Px multiplied by H square, which also this term has Hx Px Hx into Px multiplied by H square. So, this is also has the same prefactor of minus half, but this minus gets added with a plus. So, this term results in this second term results in a plus Px H square by 2 mu into Hx, and the first term actually is now half minus 1/6. So, it is essentially 1/3 mu H cube into Pxx. So, this is what you get, del H del T minus Px H square by 2 mu into Hx is this. So, you do a transposition and you get del H del T minus H square by mu into Px Hx minus 1/3 mu H cube Pxx is equal to 0. And this one. So, I will just rewrite the expression for taking it into a more compact form. H square by mu px hx minus 1/3 mu h cube pxx is equal to 0. We just write del h del t minus 1/3 mu to 3 h square px hx plus h cube pxx is equal to 0. What I would really request you, and this is what I tell also to my classroom students when I teach this here at Kharagpur, is that please go through this derivation. You do it yourself once other than just listening to it. So, note down the best approach to go about it would be to note down the whole sequence of derivation, take a pen and a paper and do the whole sequence once clearly. I am sure it will make things very clear to you. There is nothing great thing is there, only a couple of manipulation from this form to that form. You use continuity some place, you use some other equation some place. So, apparently if you are just sitting back relaxing and listening to this lecture, I am sure it will hardly make any sense, but the moment you take a pen and a paper and try to do this derivations yourself, I am sure it will be very clear to you. There is nothing really great that is going on over here. Okay. And so, if you combine this now, you find that this can be very compactly written as this can be very compact nicely and compactly written as minus 1/3 3 mu into h cube px x is equal to 0. So, this is the final characteristic, this is the final equation in a in the conservative form. Now, we need to worry about what is P. It is the non-gravitational pressure, which is essentially P plus phi. Now, there are two things. When we had been talking about the instability of a surface, we had been talking about the two types of pressure or two types of factor. One is the Laplace pressure due to the curvature. So, P will come from the Laplace pressure. So, this will be provided from the Laplace pressure. And phi essentially takes care of the interfacial interaction. So, we will get the expression of phi from the interfacial interaction. Now, we are running out of time in today's class. So, I would request all of you to please go through these derivations up to this point in great detail, so that you are conversant with what is happening, you understand how exactly this whole thing comes, and we will pick up our subsequent discussion from this point. Thank you.